All right. We are on page 319. Yesterday I mentioned near the end of our time that in one of the reactions we had hydronium that was produced. I don't remember if I actually told you the name hydronium, but I did remember telling you about heavy water. Same thing. Okay, but that is a polyatomic ion that you need to be able to recognize. So when you see it, heavy water, hydronium, or H3O positive. I mentioned how that water, and the term in the middle of page 319, I said we'd get to it today, is that phrase, you see, amphiprotic. That's the way it's pronounced, amphiprotic. Another phrase that's sometimes used by chemists is amphoteric. They mean the same thing, and they're used interchangeably. As a matter of fact, in this book, they do include that. Okay, it's in the paragraph just below amphiprotic, where it says amphoteric. So when you're reading, like they say, when you're reading some sources, it may say amphoteric, it may say amphiprotic. It basically means the same thing. And do you remember what that it means? Definition's right there if you forgot. But what does it mean if something is amphoteric or amphiprotic?
Act as an acid or a base.
It can act as either, right? It's an acid or a base. So in the question, just because you see something, and most typically it's water, just because you see a reaction that includes water, and if you're told that it's an acid-base reaction, you can't tell whether water is an acid or a base until you look into the whole reaction further. Because water is the most common example of an amphoteric or amphiprotic compound, because it can act as a acid or a base. So, in fact, let me go ahead and write the equation. Let's look at that equation one more time on how we determined how, or which was the acid or the base based upon how the molecules changed. We looked at proton donating and proton accepting. We had HCl, H2O, produces H3O and chlorine. Okay. There's said in here we can't tell necessarily that this is an acid or base because we know it's amphoteric or amphiprotic. Looking over, if you know that HCl is hydrochloric acid, the biggest hint that this is the acid is that it's called hydrochloric acid, not hydrochloric base, or not hydrochloric. Sorry, hydrochloric acid. That we will consider what we see on both sides and how the molecules have changed. Generally, one of the molecules is going to change by losing a hydrogen ion. The other one's going to change by gaining a hydrogen ion. Just going to notice here there's hydrogen and chlorine combined over here, a lone chlorine over here. I can make a pretty good guess that this molecule here has changed into this ion over here. And in like manner, that this H3O has changed into, or excuse me, H2O has changed into H3O. In this case, we're going to add a proton to go from H2O to H3O. And to go from HCl to just straight chlorine, we're going to lose a proton. So by our definition of what is an acid or a base, remember that an acid is a proton, fill in the blank. That would have been on today's desk work quiz. An acid is a proton donor, and a base is a proton acceptor. Right. So which one donates a proton? Which one loses a proton? Hydrochloric acid loses the proton to become chlorine. So this would be our acid by virtue of the fact that it lost a proton. And H3O, in this case water, gains a proton, so it's going to act as the base. So the base hydrochloric acid, or excuse me, the acid hydrochloric acid and the base water produce hydronium and chlorine ions, or chlorides. Okay? Now, to show the amphiprotic nature, they list a second reaction in here, H2O and ammonia react to produce ammonium and hydroxides. Again, the intuitive method here is to look at it and say, do I see something which changes by losing a hydrogen, when something that changes by gaining a hydrogen? H2O, what do you think and over here, okay, let's start with the obvious one. NH4 and NH3, right? So NH3, to go from NH3 to NH4, it gains a proton. And water, to become hydroxide, loses a hydrogen, loses a proton. Remember, protons are hydrogens. So H2O losing a proton would just be HO or OH. See that? You can think of water sometimes. The reason why we don't write it as HOH is because it's a covalent molecule, it's not an ionic molecule. Hydroxides are an ion. We don't write it HOH, but think about it, it's the same. H2O is two hydrogens and an oxygen. Actually, if we want to be technical with our three-dimensional knowledge now, we can go right? H2O. If I take one of the H's off, what am I left with? Just OH. So water loses a proton to become hydroxide, and ammonia gains a proton to become ammonium. So again, in this case, water acts as the acid, and ammonia acts as the base. See that here? Water donates the proton, or here donate means to receive the proton, excuse me, to become H3O. Here, water donates the proton to become OH. So it acts in both ways. It's amphoteric and for product. The next section here, talking about behaviors of ionic compounds in aqueous solutions. We've talked about that before. It's basically dissolving. What happens when you dissolve an ionic compound in water? Classic example, we'll keep going back to it, with sodium chloride. Sodium and chlorine are held together because sodium has a positive charge and chlorine has a negative charge, the ions. So the sodium ion and chlorine ion have opposite charges, and they're attracted to one another by the electromagnetic force. Opposite charges attract. They're stuck together. When we then take this and put it with water molecules all around it, again, we submerge this and it's completely surrounded by water molecules. Think of the water molecules as acting like piranha. They get in there and start chopping everything up, tearing it apart. And they're able to force themselves between the sodium and the chlorine and put space between them to make them free-floating ions in water. And because they're now free-floating ions in water, they have the ability to transfer electrical charge. Remember, for electricity to flow, you've got to have charges that can move. When sodium and chlorine are bound together, their charges are neutralizing each other. There's no charge, there's no net charge, and there's no ability for it to move. Here you've got positive chunks and negative chunks floating around in water. Now they're separated, now they can move. Now we can get a current to pass through that. Also, remember too, that I think it was in Module 5, that water has partial positives and partial negatives around it, right? That's part of how this all works. Water is able to force itself up here between, because let's see how to do it the right way. It's going to be kind of upside down from the way we're used to orienting it. Okay. But because of the partial charges here, the hydrogen is going to tend to be partial positive, and the unbonded pairs are going to tend to be partial negative. So it has a net charge of 0, but remember the electronegativity, in this case, of oxygen is greater than hydrogen. It's going to tend to want to hold those electrons towards the oxygen. When it does that, it's going to favor then, since this side is partial negative, it's going to attract the positive side of the sodiums. The sodiums are positive, but they're going to be attracted to the positive, to the negative side of the oxygen molecule. And the negative chlorines are going to be kind of attracted to the positive side. So you can see how water could force its way in there and go in between them. It's got that additional force that breaks up the sodium chloride. Now the sodium and the chlorine ions are free to move in solution because they have water between them, separating them. Middle of page 320, when ionic compounds dissolve, they split into their constituent ions. Nothing relative about that. You write the ionic forms. They're in solution now, and again, they can conduct a charge. That's all review, right? This here is a review from yesterday, which was new yesterday. This is a review from many modules ago. Just wanted to make sure that you had this in mind as we talk about the transference of protons. It's important to remember this. Okay. Now, some of these sections to me are very repetitive, but it's kind of like stoichiometry, kind of covering the same ground several different ways. So we're just going to continue to press through the text and do the way that they're presenting it, but I may, take side trails, rabbit trails and sidetrack at a time, now and then. But we are on 320, identifying acids and bases in chemical reactions. And what they're doing is taking this same concept here and kind of expanding it out. One of the points you need to remember is that acids are covalent molecules, and that whenever we look at these reactions, if you can look and find the covalents and the ionics pretty quickly, that'll give you a good head start and figure out which is the acid and which is the base. Just looking at the examples, they just give us several examples, so we'll walk through those on the board together. We've got sulfuric acid, H2SO4. For brevity up here, I'm going to drop the phase symbols. It's calcium carbonate. We have to produce calcium. CO3. And HSO4. That's also negative, correct? Yeah. All right. So we've got sulfuric acid and calcium carbonate react to produce calcium. We've got the HCO3 and HSO4 ions. Now, one of the things that may be confusing, if you looked at both of these molecules and you had to say, are they ionic or covalent, what would you tend to say? Well, isn't this a polyatomic ion? Isn't this a polyatomic ion? Don't they appear at first to be both ionic? This is our acid right here, and it's the hydrogens that cause this to act in a kind of a funky way. So what I want you to do is, as you look at these, and you're trying to identify the acids and the bases, and if you think that the acids, if you remember that the acids are covalent, look for the obvious ionic. It's not going to include a leading hydrogen. That's one of the ways to find out which is the acid. Acids tend to have a leading hydrogen in their molecular formula. So the fact that it has an H2SO4, I might forget that it's sulfuric acid, but because it has a leading hydrogen, I'm going to tend to think that that's an acid. Let me look at the other things that are involved in the reaction. Is it clearly an ionic compound? Calcium carbonate. Yes, it is. It's clearly an ionic. What's going to happen when this goes into reaction? Let's kind of take it into steps. We start with H2SO4 and calcium carbonate. When they go into solution, we're going to have H2SO4 plus, let's take the ionic and break it down into its parts. Going to be calcium, right? And carbonate. You guys remember this stuff? Okay. All I've done here is I've chosen to write it this way by putting in a bracket, so I can remember. What did this become? Well, this is going to stay the same. What did this become? I break it down in solution into its ions. So look at what this is going to produce. Same production over here. Let me go ahead and write the same products of reaction. Ca2 plus HCO3 negative plus HSO4 negative. So this is what I start with. I write the acid again, and I break down the ionic compound into its constituent ions. Now let me go through and look. Where do I see something that receives a hydrogen, accepts a hydrogen, and where do I see something that donates a hydrogen? Well, the easy thing to do, first of all, is look for where do you have something that's the same on both sides, that doesn't change. In this case, the calcium ion, if I say when I put calcium carbonate in solution, it's going to break into its constituent ions, and I have a calcium 2 plus on this side, and I have a calcium 2 plus on that side, the calcium in and of itself is not changing, right? It doesn't lead you to the acid or the base. It doesn't give us any information when we're doing this, looking for a losing hydrogen or looking for gaining hydrogen. Because technically, on both sides, it doesn't have an effect. It doesn't change. So now I'm just checking out the H2SO4 and the CO3 and seeing how they change. Look for a visual cue. Look for this molecule here, the CO3. Do I see it on the product side? I do, don't I? Let me draw the lines to it. This matches with that. What's happened to it? It has done what? To go from here to here, I've had to do what? I've had to add a proton, right? Remember, a proton is a hydrogen ion. I've had to add a hydrogen to this to get this. So it's receiving the proton, it's accepting the proton. Therefore, in this case, this ion is acting as an acid or a base. Which is it?
Acid.
Since it accepts the proton, proton acceptor is the base. Okay? So I've got a cue here that this right here is my base. The only thing that's not accounted for is over here. I can suspect that that's going to be my acid, my H2SO4. Again, if I know it's called sulfuric acid, boom, there it is. If I look and say, hey, it's got a leading hydrogen, it may very well be my acid. And if I note that H2SO4, for it to become HSO4, has to lose hydrogens, doesn't it? So in that transfer, it donates hydrogens. So it's losing protons to become that. And so since it's losing protons to become HSO4, it's acting as an acid. Now here's the deal. If I ask you in this reaction, what is the acid, you would hopefully come back and say the H2SO4. The sulfuric acid is my acid in this reaction. Less obvious is if I say, what is the base? Well, we said that the calcium has no change, so it doesn't lead us to tell us which is the acid or the base. However, the carbonate side does tell us that it's acting as a base, but the carbonate in its original form is not there all by itself, is it? It's part of the calcium carbonate molecule. So the answer to the question, what's the acid, is the H2SO4. What is the base? The base is the calcium carbonate. Because even though the calcium doesn't change on both sides, once we break it down, we had to break it down first. The carbonate would not be there if the calcium carbonate were not there. And so it's the calcium carbonate molecule as a whole that's acting as the base. Understand the nuance there? How I broke it down, but just because I broke it down, the only way I could break it down is if I had it in the first place. So you're tracking back to where did that part that's acting like the base come from? It came from that molecule. So this is the base. And I would hate for you to understand all of this, but then still in the exam write down, what is the base? The carbonate ion. No, it's not. That's not truly the base. The calcium carbonate is the base. Really quiet today, guys. What's up? Is this obvious, or is this don't really have a clue what you're talking about, Mr. Baker? What's going on here? Okay. You're still good with it though? You're not here going, I can't do this. This is crazy stuff. We can't do this. If anybody's there, I want to call you back from the edge. This is doable. Right now, we're just looking for visual cues. And you can see now why in the future we talk about when you're going to have a balanced reaction equation, you have to be able to break down and name your polyatomic ions, to be able to figure out how they're constructed. Everything we've done for the last 3 modules specifically are real important here. Module 5 and up is very important. Not that they're not all important, but I'm just saying 5, 6, and 7 are crucial. 5, 6, 7, and 8 are crucial to doing module 9. Again, these examples are all in the book, so if you have a question about the process and how it broke down, it's written out for you there in text format. But we're still going to just walk through them here in class as part of
I do.
presentation. Go ahead.
Do you always have the arrow going this way? Always moving
On these considerations for right now, yes.
Okay.
We're saying, starting with this reaction over here, what is acting as the acid in the base? Going in this direction. Now, in the future, remember I mentioned before about the conjugate acids and conjugate bases? Because if I were to say, okay, now looking at the reaction going the other direction, this acid, this would be the conjugate base. Why? Because as we go from this to this, the arrows point the other way, then it'll be the opposite.
But do they always face do both always face in the same way when you're identifying?
Yes, because we're considering the reaction moving in this direction.
And that you could do the other direction if you both go that way.
But if I did the opposite reaction this way, the arrows would change, and this would change to a plus, and this would change to a minus. Because whatever gains in that way loses in this way. Whatever loses in that way gains in this way. And that's why this is called, the acid hooks to the conjugate base. Because as it goes back, it goes from basic to being more acidic. It's going to add, it's going to add that proton. And this is the conjugate acid. Why? Because when it moves from here to here, it's going to lose the proton. HCl plus NaOH H2O and sodium chloride. First thing I'm going to do, I've got 2 molecules. This is a covalent molecule, isn't it? Both nonmetals. This is an ionic molecule. Now, hydroxide is the most common visual indicator you're going to have during acid-base reactions for the presence of a base. The ion, or the molecule that has the OH in it, is going to be the base. What you're basically looking for is the production of water. The hydrogen from the acid and the hydroxide from the base come together to form water. And the remainders come together as well, whatever's left over. So this is where you take hydrochloric acid and sodium hydroxide and you mix them together and you have salt water. You don't want to ingest the acid in strong concentrations. It's the same acid that's in your stomach. So those times when, remember I said last module, I've said this so many times that, okay, when you do that for real and you get the burn in your throat from the acid, the stomach acid in your throat, that's what this is, hydrochloric acid. Okay. Sodium hydroxide neutralizes that acid. So as you take sodium hydroxide with hydrochloric acid to make water, and it turns into salt water, you could take the acid, and again, don't suggest you do this, but you could take the acid, hydrochloric acid, and the base, sodium hydroxide, both of which, I would argue at certain concentrations are going to be pretty damaging to your body. Mix them together, drink it, and you're drinking salt water. because of the reaction that takes place between the two. Okay? So looking at it real quickly, I'm just going to go ahead and take this acid. I'm going to leave it in the same format, HCl. I'm going to go ahead and break down the sodium hydroxide. It must be the board, because I can't possibly go through this many markers in a week. I agree. It's tedious, isn't it? There we go. It's the best one. Let's start using this one now. So hydrochloric acid. I'm going to break down this into the sodium and the hydroxide. And maybe now it's a little easier to see the transformation that's taking place. I hadn't thought of this before, but let me write this one more way. Not to confuse it, but for some people this might help you see it. If you know that sodium hydroxide is just a sodium ion and hydroxide polyatomic ion, sodium chloride, right, is just Na and Cl, right? What doesn't change from the way I've written it this time? What doesn't change from side to side? Both have the sodium ions in there, right? So for purposes for right now, considering acids and bases, I'm not going to consider the sodium. Right now, that's just a distraction. So I'm going to line through that. I'm going to look for something that loses a hydrogen and something that gains a hydrogen. HCl, what does it pair to? What's its visual partner on the other side? Chlorine, right? And for me to go from HCl to Cl, what do I need to do? Lose a proton. If it loses a proton, then it must be the acid. So it's no shock that hydrochloric acid is the acid. It's what is shocking is Hunter Judd is a Judd. Okay, if you know his name, you can tell where he's from. All right, so now let's look at the other. What's left? OH and H2O. I'm going to assume that there's some magic happening here, right? And what's that magic? To go from OH to H2O, you need to add a proton. Remember, when I write proton, all I'm saying is adding a hydrogen ion. They're the same thing. A proton and a hydrogen ion are the same thing. So I could say lose a proton or lose a hydrogen. Gain a proton, same thing as gain a hydrogen. So since the hydroxide acts as a base, the acid is the hydrochloric acid, and the base is this whole molecule of sodium hydroxide. Granted, the OH portion is what's going to donate, or excuse me, is going to accept the proton, but you get it by virtue of having the whole sodium hydroxide molecule. So hydrochloric acid, sodium hydroxide base, which makes water the conjugate acid and sodium chloride, this whole molecule, sodium chloride, as the conjugate base. What does that mean? If we ran the reaction in the other way, that means that water here would act as the acid and sodium chloride would act as the base. Shall we do one more? The book does. Let's go ahead. From 322, for those that are following along, or 320 for those of you that are drooling. You haven't quite kept up with us. Which today's not so bad. Everybody seems to have two eyes today. It's good. It's two. You know what that refers to, right? Sometimes I see no eyes. Sometimes I see one eye struggling to be seen. So 2HNO3. appreciated your extended presence today. Thank you. I'm having a great time. Don't walk into the ladder. Show up too late. I said, have fun. He's like, okay, backing up. All right, last one. What's taking place here? Well, again, I jump right into this. I see an ionic compound right here with the magnesium hydroxide. Remember, hydroxides are going to be the -1. We got 2 of them. Magnesium is +2. It's a column 2 element. So I know that that's going to break down. This, I'm assuming, is going to be my acid. I'm going to go ahead and keep it together. I'm going to rewrite this as 2HNO3 plus bracket magnesium 2 plus 2 OH negatives, right? To produce, take the magnesium nitrate, break it down. We've got 2 NO3s plus 2 H2Os. Nothing fancy about this. All I'm just showing is I break down magnesium and hydroxides that form this molecule. And then on this side, it produces magnesium nitrates, which have those components. And right now, the big deal is not figuring out the exact numbers. The deal is which is the acid and which is the base. So after I go through and break it down, look for those things which are the same on both sides. Again, it's the magnesium ions in this case, magnesium ions that are on both sides. Now look for those things that accept and those things that lose protons. I've told you before to look first for OHs becoming H2O, right? Look for hydroxides to become water. Because the acids are going to tend to give up the hydrogens. And if there's a hydroxide, it's going to take that hydrogen and become water. So we see the OH here and the H2O there. And OH becomes H2O by adding a proton in that direction. Looking over here at the HNO3, HNO3 becomes NO3 by losing a proton, by losing a hydrogen. Right? So I've accounted for everything, right? Everything is either staying the same, in this case the magnesium ions, or HNO3, it's losing a proton to become NO3, or hydroxide, OH, is gaining a proton to become water. So, proton donor is my acid, and the proton receiver, right here, is my magnesium hydroxide. This is my base. See at the bottom of 322, it says it's important to be able to analyze acid-base equations in this way because it builds upon so many concepts that we have learned. First, you have to be able to name the ionic compounds. Second, you have to be able to interpret chemical formulas of ionic compounds in terms of their charges. Third, you have to be able to recognize what subscripts and parentheses in a chemical formula mean. And all of that, as it says there, that's all review. Everything up to that point is review of things we've done before. The only new skill that you need here is the ability to determine where the hydrogen ions went. It's the only thing we're adding. So everything we've done up here, we've done before in other modules. The only thing we're adding is this part here. Who's losing and who's gaining protons. All right, so we are down to on your owns 9, 1, 2, and 3. I would encourage you to do those. Let me take a look in the back and see where we are in terms of study guide and practice problems. So review questions 1, 2, and 3 are doable. Practice problems. You probably can do 1 through, some of you can do 1 through 4, but it's gonna be balancing the equations. So we haven't done any of those through the examples yet, but if you can break them down, you can probably do the balancing. So I'd encourage you to give those a shot, but don't be too frustrated. We haven't done an example of how to do that yet. Okay.